Hello everyone. So today we're going to start on continue on 13.2. So last one we get to look at three different examples where we use matrix exponential to try to solve a system of differential equation. So lucky for us, all three of them, the matrix exponential actually come out to be relatively easy to find. Two of them actually have a diagonal matrix, so even though one of them involved complex numbers, it wasn't that hard to figure out what E to A, TA is. And then we have this particular one right here, which is 1101, which we actually find out that A to J power is actually a very simple pattern, which then result in a very relatively easy matrix E to TA. So of course, that's not always going to be the case. I mean, I don't know about you, but try to go through this process to find a pattern for A to J, and then try to form the summation and try to show that what is summation converges to doesn't seem too easy. I mean, most of these examples that we've done are simply designed to work out perfectly, but just try to find this pattern of A to J could be something that's hard to do. And then try to figure out like at least some of these, could be potential up to 4. Well, technically depend on how big the matrix is. Many like power series or infinite series, and try to figure out whether they converge to something doesn't seem like easy things to do. So is there a better way to try to calculate matrix exponential? And there is. The tricky part about it is that it is something that we already know how to do, or using something that we already know how to do. And that's the following. Next we're going to talk about is the relationship between matrix exponential and eigenvalue eigenvectors. So there's a definitive connection between these two things, and we're going to try to exploit that and use that to help us find matrix exponential. Now, but of course, we'll talk about major issue why it's work out for most cases, but definitely not work out for all cases. So we'll get to that. But let's see if we can identify the direction between the relationship between these two things. So in 13.2, this section, we just learned the following. If we're given a differential equation in this form with an initial condition, vector x of 0 equal to x sub 0. So remember in here, A is a constant matrix. Then we know the solution is vector x equal to e to ta vector x sub 0. However, we also learned in 13.1 that if we're given a system of differential equation in matrix form with initial condition, with same initial condition, the solution is this. Now, since the solution set to a given differential system of differential equation must be unique. Now, important to understand, they are infinite solution, but these are specific to a initial condition. And therefore, the solution must be a unique solution, a particular solution, subject to that initial condition. So therefore, it cannot be two different answers. But we do now look at this and have two different formula that can generate the same exact solution. So therefore, meaning that these two formula must be the same. It implies vector x must equal to e to ta vector x sub 0, which also must equal to u lambda t u inverse times x sub 0. And if I look this correctly, that would tell me that this and this must be the same. And that gives us a formula to allow me to generate matrix exponential, the e to the ta. But of course, if that's the case, then we already know u lambda sub t u inverse already. So why do we need to know matrix exponential? Well, because of following. Note. While for any given n by n matrix A, e to ta must exist. Why? Because we stated that in theorem 13.2.1, saying that any kind of square matrix must have a matrix exponential, e to ta. However, for any given matrix, for any given n by n matrix A, matrix U does not have to have an inverse. Implied, for some matrix A, U inverse does not exist. And when that is the case, what does that mean? Does that mean that e to ta not exist? No, e to ta must exist. We already established that from 13.2.1 theorem. So what does it mean is that, meaning in those cases, in this cases when u inverse does not exist, we cannot use this formula to find e to ta. Therefore, if u inverse does not exist for matrix A, we cannot use this formula to find e to the ta. E to ta still exists. We just can't use this formula. We have to use some other formula. And you might be thinking like, okay, when would this happen? Well, simple. Actually, you already know what had to happen. I already pointed out to you. Let A equal to 1, 1, 0, 1. Then its eigenvalues is just lambda equal to 1. It's a repeated eigenvalue. You can definitely see that. If you do the determinant of 1 minus lambda, 1, 0, 1 minus lambda, that becomes 1 minus lambda times 1 minus lambda. If you set that equal to 0, therefore give you a repeated value of 1. Right there. It doesn't have 2 eigenvalue. And because it doesn't have 2 eigenvalue, we can now try to figure out what is the eigenvector that go with it. So the eigenvector will be this matrix. That implies that v equal to 0. So therefore, I can say vector u would be any vector that's in the form of something 0. I'm going to say 1. And therefore, tell me that matrix U in this case could be 1, 0, 1, 0 because it has a repeated eigenvalue. And U inverse does not exist. Because this matrix has an entire row of 0. And therefore is not invertible. Now, In this case, notice we do know what e to ta is. We have figured it out. So even though this formula u lambda sub t u inverse does not work because they failed to have a u inverse, e to ta still exists. Remember, we found that. I believe, let me see what the e to ta is this thing right here. E to t, t e to t, 0 e to t. Okay, so important to understand is that even if this formula failed to work, because of most likely because u inverse doesn't exist, because this matrix A's have a repeated eigenvalue, I can still find e to ta through other means. Okay, just because this formula doesn't work doesn't mean e to ta does not exist. E to ta must exist. Okay, it just means we have to find some other way to actually calculate it. With that being said, how about we try to actually use this formula to calculate a e to ta? So I have some example that we can look at. So let's I guess give it a try. Okay. So, oops. All right. Let's try this one first. So this one would be just finding e to ta. Let a equal to 1405. Find e to ta. Now, I could definitely try to see if I can find a pattern for a to j, and then hopefully that pattern would lead into us being able to find a summation, and then be able to find out what the summation converges to, and then use it to find e to ta. But I would much rather use the eigenvalue, especially in this case. I'm kind of convinced that this would not run into issue of having a repeated eigenvalue. So I'm going to do this. I'm going to do find the eigenvalue. Which is equal to this. Which is just equal to 1 minus lambda times 5 minus lambda. So if I set that equal to 0, it gives me lambda 1 equal to 1 and lambda 2 equal to 5. So that's pretty simple. And then I'm going to try to find my eigenvalue so that I can form my formula. So my eigenvector, my eigenvalue is 1, so therefore my matrix is 0, 4, 0, 4 times uv equal to 0, 0. So that result in 4v equal to 0. So therefore tell me v equal to 0. So therefore I'm going to go and say that vector u1 will just be 1, 0. Because I know v has to be 0, but u can be anything. So I'm just going to say u is 1. And lambda 2 equal to 5. So therefore I have 1 minus 5, which is negative 4, 4. And then 0, 5 minus 5 is 0. So therefore you have this. So that results in negative 4u plus 4v equal to 0. So I'm going to go ahead and say vector u2 would be equal to 1, 1. Or 2, 2, or 3, 3, or pi, pi, or whatever. But I would just say 1, 1, which is easy. So therefore, now I'm ready to form my matrix. So this tells me that matrix U is going to be 1, 1, 0, 1. Oh, actually, 1, 1, 1, 0. Because I will put, no, actually, you know what? No, I mean, I did put U1 first. So U will be 1, 0, and then 1, 1. So that makes sense. Then what is U inverse? So actually it's not too hard to do because the determinant here is 1 times 1 minus 0 times 1, which is 1. So therefore we can totally ignore the 1 over AD minus BC part because that just becomes 1. And then the formula basically tells me to flip-flop A and D, which they're both the same, so therefore they're both 1. And then negate B and C, so therefore become this. And so now I'm ready to form my E to TA. My E to TA is going to be equal to matrix U, lambda sub t, U inverse. So therefore become 1, 1, 0, 1 multiplied by E to t 0, 0, E to 5t. And then 1, negative 1, 0, 1. So really depends on how you want to multiply this together. I guess I'll just go multiply the first two things together. So therefore 1, 1 dot product E to t 0 will be E to t. 1, 1 dot product 0 E to 5t is E to 5t. And then 0, 1 dot product E to t 0 give you 0. 0, 1 dot product E to E0 to 5t is E to 5t. So that's this. And now I have the dot product U inverse. So therefore, this dot this, there will be E to t. And then this dot this would be negative E to t plus E to 5t. And then this would be 0. And this would be E to 5t. So sim to me, this is what E to ta is. And I'm actually glad that I didn't use a to j power and then try to form the summation and then try to find the what the summation converges to, because it might be hard to figure out what this corner term is if I look at the summation and have to try to figure out that the summation actually add into negative E to t plus E to 5t. That might not be too easy to figure out what that is. Good thing we didn't do that. All right. So now, of course, then I can try to solve a differential equation using this. So what if now I'm going to say this? Maybe I'll say this is, actually, I'm just going to add on to the problem. So what if now I ask you to solve this? Um, 1405. And I'm just make up an initial condition. So now what would the answer to this be? So I'm going to call this B. Yeah, I'm going to call this A just for easy reference. Then, well, we already know what the answer is because this is my matrix A and I know E to TA. So therefore, in this case, I'm going to say that the answer will have to be this. And so now I can say this is this dot product this, so it'll be 2 E to t plus E to t minus E to 5t, because that multiplied by negative 1. And then this multiplied by this will be negative E to 5t. So if I look at this correctly, that tell me is 3 E to t minus E to 5t, and then negative E to 5t. That will be my answer, vector x. All right. We probably have time for one more example, so let's do one more. So let's try this one. Let's say we're going to do the following. I'm going to say let A equal to 5, negative 3, 1, 1. I'm going to go and do the same thing. A, I'm going to go and ask you to find E to TA. I'm going to go and say using this formula. I might say, well. Alright, so let's go and try to figure this out. So let's start with the eigenvalue. So the determinant of A minus I lambda I must equal to 0. So therefore tell me is 5 minus lambda multiplied by 1 minus lambda minus 1 times negative 3 equal to 0. I mean, by now you should be able to kind of write this out without going through all this little step in between. We have done eigenvalue for 2x2 matrix enough time that you should be able to do that. So that come out to be 5 times 1 is 5, minus 1 lambda minus 5 lambda is minus 6 lambda plus lambda square. plus look like plus 3 equal to 0. So therefore, that tell me is lambda squared minus 6 lambda plus 8 equal to 0. So that come out to be lambda equal to lambda 1 equal to 2 and lambda 2 equal to 4. 2 and 4. You can easily factor that into lambda minus 2 times lambda minus 4. So therefore, is lambda 1 and lambda 2 are 2 and 4. So let's find our eigenvector. So let's say lambda 1 is 2. Then what we have would be 3, negative 3, 1, negative 1 times uv equal to 0, 0. Once again, at this point, you should be able to find the eigenvector relatively easy and quick because, I mean, we have been doing this for a while. So that come out to be vector u1 must equal to 1, 1. Okay. And lambda 2 is 4. So therefore that come out to be 5 minus 4 is 1, negative 3. And then bottom would be 1. And then 1 minus 4 is negative 3 again of uv equal to 0, 0. So therefore this one will be lambda 2. So I guess lambda 2 could be 3, 1. 3 times 1 plus negative 3 times 1 would be 0. So therefore my matrix U would be this. Matrix U would equal to 1, 1, 3, 1. So therefore matrix U inverse would actually be equal to 1 over, let's see, the determinant of this is 1 minus 3. So negative 2, 1 over negative 2. And then flip-flop these two, which they're exactly the same, negate these two, which they now both become negative. I am actually going to do the following. I'm going to actually leave the 1/2, but I do multiply the negative in, just so that I can kind of don't worry about the negative and just leave it inside the matrix. And now I'm ready to find e to ta using the formula. So e to ta would equal to u multiplied by lambda t, which is e to 2t, 0, 0, e to 4t, and then multiplied by the inverse matrix. Okay, and of course I sure recommend that you pause the video right now and go and try to carry out this multiplication and see what you got, okay? So I'm going to just keep multiplying them. So I'm going to just do this. So therefore, this time this would be e to 2t. This time this is 3 e to the 4t. This time this is e to 2t. And this time this is e to 4t. All right. So, let me see what we got. So therefore would be this time this and then time the 1/2. So therefore would be 1/2 negative because negative 1 e to the 2t, and then this would be plus 3/2 e to the 4t. Okay, now if we multiply this to this, I have 3 over 2 e to 2t minus 3 over 2 e to the 4t. And this one would be negative 1/2 e to 2t plus 1/2 e to 4t. And this last one would be 3 over 2 e to 2t and then minus 1/2 e to the 4t. After you do the matrix multiplication. And so that would be my e to ta right here. Yeah, trust me, it's probably not a good idea to try to figure it out what it is through a summation and a power series and a convergence of the power series. It's probably not going to be too easy to figure this out. I would not recommend it, of course. So now we can actually try to use this to help us find the solution. And if you think about it, wasn't the same thing that we do in 13.1 once I introduced you to this formula? Right here. Yes, it is exactly the same thing. We are actually not doing anything different other than that we calling this three thing multiplied together and give it a name called e to ta. That's all that is for now, until we figured out what happened when we have repeated eigenvalue. Okay, so that's what we work toward. Okay, but for now it is exactly kind of the same thing. So I think we'll finish after this this one part. So let's say d vector x over dt equal to 5, negative 3, 1, 1 vector x with, let's say, x vector x of 0 equal to 1, negative 2. Let's try to solve for vector x. And since we have our matrix exponential already, so that's pretty easy. That just means vector x is equal to e to ta multiplied by 1, negative 2. So that just means this massive matrix multiplied by 1, negative 2. Now, it might seem like quite complicated, but it actually is not, because all you really have to do is just focus on the terms they involve. And if you look at this matrix right here, even though it looks like it's complicated with binomial on every single entry, and there are 4 of them, and then I have to multiply that by the vector 1, negative 2. How are we going to do this? You have to keep in mind, you are doing nothing more than 2 separate terms. What those 2 separate terms are? E to 2t and e to 4t. So you're basically just keeping track of the the coefficient and try to combine the coefficient properly. That's all that is. So keep that, focus on that, and you'll find out it's not that hard to finish. Okay, so this would just equal to 1/2 e to 2t plus 3 over 2 e to 4t. Negative 2 times this thing become minus 3 e to 2t plus 3 e to 4t. And then take the bottom row, multiply that, give me negative 1/2 e to 2t plus 1/2 e to 4t. And then negative 2 of that become minus 3 e to 2t minus, plus actually, because double negative, e to 4t. And if you think about it, all you're doing is combining the coefficient for e to the 2t together, and then combine the coefficient for e to the 4t together. Same thing happened on the bottom, e to 2t, combine to e to 2t, and then e to the 4t, combine to e to the 4t. Which is a 1 in this case. So therefore, negative 1/2 minus 3 is negative 7 over 2, e to 2t. 3 over 2 plus 3, so that's 3 plus 6, so it's 9. 9 over 2, e to 4t. Negative 1/2 minus 3 were established as negative 7 over 2 e to 2t. 1/2 plus 1 is 3/2 e to 4t. That's your answers right there. That will be it. I'm going to stop right here because 29 minutes already. So we're going to continue on our next video. All right. Talk to you guys later. Bye-bye.